Alright, in our previous example 11.4, we are considering deformable system. Okay, means that the shape of the original system might change due to the motion of the objects. Okay, now let's focus on the non-deformable system. The system whereby the shape of it will not change, okay, even though it is in motion. Okay, let's consider this object, rigid object here. Okay, let's consider this rigid object rotating about a fixed axis that is along the axis, okay, of our coordinate system as shown here. Okay, let's determine the angular momentum of this object since it is in rotation, right, with omega, okay, along the axis, right. Each particle, okay, every single particle within this object, okay, rotates in xy plane about the z-axis here, okay, with the same angular speed omega. The angular momentum, okay, for this particular object mi here will be mvr. So remember, okay, mvr, okay, where is actually equivalent to the v itself is r omega. Okay, that is how we have this mi ri squared omega. Alright, then this is stand for v, okay. Alright, then L along z-axis, angular momentum along z-axis, means that L total for each item within this object, right? So we're going to have sum of mi ri squared times with the omega. Okay, so since omega is constant for every single particle within this solid object, so we can factorize omega here. So we are left with this pattern. And we know that L is equivalent to, here is what? Moment of inertia, right? mr squared. So this one is actually moment of inertia. So we are rephrasing our equation now into L along z, okay, angular momentum along z axis is equivalent to moment inertia times with the omega. Alright, to have differentiation of L along z to the respect of time, okay, we may do I d omega over dt. Omega over dt, d omega over dt is actually alpha, angular acceleration. So now we have a new term of sum of torque external on our system or object is equivalent to I alpha, okay, and sum of torque, remember torque is equivalent to R cross F, right? Okay, and angular momentum is equivalent to I omega. The direction of the angular momentum according to the direction of the omega. How to determine the direction of the omega? Use Grab's rule, or also known as right hand rule. Place your forefinger along your R, cross towards your V. Then you're going to have direction of your omega, which is along your thumb. Example 11.5, the seesaw. A father of mass MF and his daughter of mass MD sit on opposite ends of a seesaw at equal distances from the pivot at the center. The seesaw is modeled as a rigid rod of mass M and length and is pivoted without friction. At a given moment, the combination rotates in a vertical plane with an angular speed of omega, shown here, right? So this is our omega, okay? Find an expression for the magnitude of the system's angular momentum. Right, so I for a long road where the axis of rotation is at the center of it, according to the table, okay, from your textbook, is equivalent to half is equivalent to 1 over 12 ml squared, and moment of inertia for the father, okay, is equivalent to ml over 2 squared, because this is the r, okay, for the m of the father. For the daughter also the same, it's l over 2 squared. This is the r. The common the general equation of moment of inertia is mr squared, right? So this is mass of the father, r of the father, and here is m of the daughter, r of the daughter. Okay, this is for long thin rod, okay, with the axis of rotation at the center. Okay, so the I of it, the moment of inertia of it, is 1 over 12 ml squared. Right, so sum of all of this, you will get L squared over 4, K m over 3 plus m father plus m daughter. So as we know, angular momentum is equivalent to I omega. Okay, so I, okay, this one here times with the omega. This is a term for the angular momentum for the system that we have just now. Alright, B. Find an expression for the magnitude of the angular acceleration of the system when the seesaw makes an angle theta with the horizontal. Right, so we are going to consider torque due to the father, torque produced due to the daughter, okay, and then we are going to have sum of the torque external, then figure out the alpha finally. Okay, so let's take a look one by one. So torque produced due to the weight of the father, okay, the father, the weight of it here, the direction of the possible rotation due to the father in this direction. Okay, so if you are using 3D XYZ axis, you will see your direction of torque due to the father is out of the page. Okay, use grabs rule. Okay, place your 4 fingers along the D, which is the here, the half length here of the total length for the rod here, okay, the seesaw, right, times with the force of this father. So you're going to have your thumb pointing out of this plane, okay, so out of the page we call it, or in terms of direction, clockwise direction or counterclockwise, this is actually counterclockwise direction. Okay, for the daughter, okay, due to the weight of the daughter, right, the possible rotation that going to produce or torque produced due to the weight of the daughter in this direction, which is, according to the direction given here, is clockwise. Okay, or if you use right hand rule, you will see your thumb is pointing into the page or this plane, right? So we will have negative m daughter g L over 2 cos theta. Why is it cos theta? We want to figure out the perpendicular distance. Either you resolve the mg or you resolve the L. So if let's say you resolve the mg, you will have here the daughter, the weight of the daughter, you will have mg cos theta, and another component here, supposedly dash, isn't it? Because we are resolving. And here you have m daughter, okay, m daughter g theta is here. Okay, sin theta. Okay, and the father, okay, you have a component of mg father cos theta, and you have another one mg sin theta. Okay, so the one that going to have rotation is this one, not this one. Not this one. Yes, this one. Okay, so the torque produced due to the daughter is clockwise, so it has negative sign. The torque produced due to the weight of the father is counterclockwise direction, so it's positive sign. Alright then. So we will do the sum of the torque external is equivalent to torque due to the father plus torque produced due to the weight of the daughter, okay, which is going to be half, right, because it's half factorized outside there. It's m father minus m daughter gl cos theta. Okay, this is torque external, but our interest is actually alpha. From the previous equation that we know, okay, this is actually coming from sum of the torque external is equivalent to I alpha, moment of inertia, times with the alpha. Alright, so our alpha here is sum of torque external over I. So you may substitute the torque external is this one, the I is this one from our part A. Right. So the total angular momentum of a system is constant. Cut that part. Okay, now we are going to take a look on the analysis model, isolated system for the angular momentum. When we talk about isolated system, means that we are going to consider conservation of angular momentum. Okay, let's take a look on this statement. The total angular momentum of a system is constant in both magnitude and direction if the net external torque acting on the system is zero. That is, if the system is isolated. Okay, so means that if we want to have dl total over dt is equivalent to 0, so the one that going to be 0 is actually sum of the torque external. Okay, then delta L total will be equivalent to 0, where, okay, we can have the rearrangement. At the end of it, we're going to have conservation of angular momentum, where we have initial angular momentum is equivalent to final angular momentum. The condition is the torque must be 0, right? Then our system is truly an isolated system. Alright, so let's take a look the analysis model here for isolated system. Okay, so let's take a look on this ice skater. Alright, when his arm and legs are close to his body, the skater's moment of inertia is small. Here, I will be smaller because I is defined as mr squared. Alright, so whenever the arms, the legs is bring close to the body of the skater, okay, the R will be reduced. So the R will be reduced, the I will be reduced. Okay, consequently, when the I is reduced, right, the omega will be bigger to maintain the L. Right. So that is why the scatter going to be seems like higher in omega. Okay, more frequently rotating. Alright. because L total for the scatter here must be constant. Okay, means that okay, L initial must be equivalent to the L final. Right, that is isolated system, a conservation in angular momentum. Right, so to have this one constant and I is reduced, okay, let's say when the skater brings his arms and legs towards close to his body, then the R will be reducing. Okay, the R will be reducing. Consequence of it, to maintain this amount, if this one is reducing, then omega will be increased. Okay, that is why at this instant the scatter seems like very rapidly, okay, moving in a circular, okay, or having omega a very big amount. Okay, to slow down for the finish of his spin, the skater moves his arms and legs outward. Okay, what will happen when the legs and his arm outwards? Okay, the R will be increasing. Okay, the R will be increasing. Consequently, the I also will be increasing. If the I is increased, the omega going to be decreased. So slow down. Okay, the scatter going to be slowed down. Okay, based on this concept, conservation of angular momentum. Alright. So if let's say we are considering isolated system still, okay, for delta E of the system, it must be equivalent to 0. It means that no energy transfer across system boundary. Okay, also delta P total of the system must equivalent to 0. It means that net external force on the system is 0. Okay, delta L total also equivalent to 0. It means that net external torque on the system is 0. Because, okay, originally we have sum of transfer. Still remember this? Okay, so if to have this equivalent to 0, this one must be 0. Okay, delta P total equivalent to sum of F external times delta T. If we want to have this equivalent to 0, means that F external must be 0, right? And delta L total, okay, equivalent to 0, means that sum of torque external must equivalent to 0. So consequence of this, delta E of a system means E final minus E initial, okay, means that E final is equivalent to E initial. This means delta P means P final minus P initial equivalent to 0. Consequence of it, P final equivalent to P initial. This means right, so equivalent to 0, so we have L final equivalent to L initial. So this is mean isolated system or being conservation of energy, momentum, and angular momentum. Right, so analysis model isolated system in terms of understanding of it. If let's say we have a system, okay, consists of angular momentum within it. This is the boundary of our system. Delta L total equivalent to 0. It means that L initial equivalent to L final. Within L itself is I omega. So I omega, I initial, omega initial, equivalent to I final, omega final, must equivalent to a constant. Okay, the angular momentum of the isolated system is a constant. This is a meaning if we can have a model or visualization in terms of system that we have. Okay, Example 11.6, formation of a neutron star. A star rotates with a period of 30 days about an axis through its center. The period is the time interval required for a point on the star's equator to make one complete revolution around the axis of rotation. After the star undergoes a supernova explosion, the stellar core, which had a radius of 10 kilometers, collapsed into a neutron star of radius 3 kilometers. Determine the period of rotations of the neutron star. Right. So, by using the concept of conservation of angular momentum, okay, now our omega, okay, is distance travel over time taken. So distance travel is 2 pi for a circle, right? Then time taken is period, okay? Go the same for the final omega. And our moment of inertia is equivalent to km Ri squared. Alright, K is a constant. It's equivalent to 2 over 3 for solid sphere. So for the shape of the neutron star, let's put it as general, a constant K. Alright, so kmri squared. Okay, this is the omega initial. Kmr final squared. This is our omega final. Alright, so from here we can simplify the equation. Okay, so we are left with this, right? So we are left with this. Then substitute the information given to us. Okay, then you will have 2.7 times 10 to the power of negative 6 days, or in terms of second, it's only 0.23 second. Alright, example 11.7, the merry-go-round. A horizontal platform in the shape of a circular disc rotates freely in a horizontal plane about a frictionless vertical axle. The platform has a mass of 100 kg and radius of 2 meter. A student whose mass is 60 kg walks slowly from the rim of the disc towards its center. If the angular speed of the system is 2 radian per second, when the student is at the rim, what is the angular speed when she reaches a point R, 0.5 meter from the center? Okay, by make use of conservation of angular momentum concept, okay, now we're going to use this one. The I initial will be I of the disc of the merry-go-round plus I of the student, okay, times with the omega initial of the system, right? And goes the same for the I final, just that the R might be changed, okay? So the R for the student will be new R. You see here, this capital R is the radius of the merry-go-round, the disc. But here we have new R, small r, because the student is in motion, right? Moving. So the R already changed. Okay, so omega final, right? So since our interest is omega final, rearrange the equation, you will have this method. So from here, substitute the information of the I for the moment of inertia for the disc of the merry-go-round plate, okay? But for the student, okay, initially is at 2 meter, but finally is 0.5 meter. Okay, from here we're going to have omega final is equivalent to 4.1 radian per second. That's all from me. Thank you very much for watching. Do not hesitate to ask any question regarding this lecture. That's all. Assalamualaikum.